Now we want to talk about designing electrochemical cells. So we know that the cell potential informs how useful is our kind of electrochemical cell. What can we do with it? What is this driving force for electrons? And so we want to think about what sort of control do we have when it comes to creating a cell, and think about how does that affect the cell potential. So some of the things that we have control over is what are the half reactions in the cell? That determines the chemistry. Are you doing zinc and copper, or is it copper and silver? Maybe, right? What are the pairs? What is the actual chemistry that's going on? Once you decide that, what are you going to use for the electrode material? What are you going to use for your electrolyte solutes? So it ends up, for those, that's actually, you really have kind of one choice or one kind of thing to decide. But once you decide it, it's once you determine it, that's not a ton of control that you have. Electrolyte concentrations, you do have control over. Say you're going to use copper 2 sulfate. Do you do 2 molar or do you do 0.02 molar, right? What do you kind of set it as? And so there's going to be a huge flexibility for this, and it can potentially have a really big effect that will be here for a later video. So for now, we're going to be looking at standard cell potentials, which means all electrolyte concentrations are going to be at 1 molar. To denote the standard cell potentials, there's going to be that little degree symbol on the E cell, which means would be like not, like we NaUGHT. So E cell not would imply that is a standard cell potential, which implies all of your concentrations are at 1 molar. And so we're going to assume that for now. We'll come back to it in a bit, but for now we're going to assume everything's just at 1 molar. So when you're dealing with choosing the electrode material, you really want to ask, do you want to use an active electrode or an inactive electrode? So for an active electrode, that word active implies that the electrode, the piece of metal, is participating in the reaction. So this would correspond, you would do this if your reactant or product in that half reaction is solid metal, because the electrode just needs to conduct electricity. So if there is a solid metal participating in the half reaction, you just use that. So for example, in our case, some of the cells that we looked at previously, we were looking at, say, copper and zinc. So you just used copper and zinc metal, and that was just the active electrode. And we saw that they, were participating in the reaction because their masses were changing, right? Reactant or product, whatever it was, their masses were changing. If you have a half reaction where both the reactant and product in that half reaction are not metals, you're going to need to use something else. So this would normally happen if you have, say, 2 ions. One ion is reducing or oxidizing into a different ion. So neither of those are going to be solid metal. So for example, you could go from like iron 3+ to iron 2+. So you would need to use what's called an inactive electrode, which just means it's not participating in the reaction. It still does need to be a metal because you want to conduct electricity. There are 2 common choices, platinum and graphite. Platinum is easy to work with, but it is extremely expensive. Graphite is very inexpensive, but is a real pain to work with. It gets really dirty. Their pieces of graphite can be really crumbly. It can just be a mess with how you have to do this. And so in our world, because we're doing everything in theory, we're going to be writing on paper, we can use platinum all we want. If you want, you can use graphite, but I prefer in my theoretical, when I'm just writing out cells, I'm living large using platinum. So if we look at, say, our zinc and copper situation, they were already part of the reaction, so we just use them as the conductive material. There's metals, they're reactants, products, whatever it is. They get electrons into and out of the reaction. They're doing what they need to do. Reactions where you're looking at, say, iron 3+ becoming iron 2+, none of those is a metal. None of those is a metal, right? They're cations, so they don't work. So you would use your inert or inactive electrode. Platinum is a good choice. You would kind of think, well, why don't we do iron? But that would be a problem because iron solid, right, iron metal, could react with iron 3+ cations or iron 2+. So basically the purpose of using platinum is that it's really bad at doing redox chemistry. Gold would be another choice. These are really kind of inert or non-reactive metals. But we don't want to use anything that would be reactive, because then you could have, your chemistry happening, say, just inside this container, and that would be a problem. Same thing would happen if you're dealing with, say, something molecules, ions that are dissolved, anything like that. You're again going to use your platinum inactive or inert electrode. And you could have used graphite, but they're living large because you're just drawing it. You just call them metal platinum, and that's for free. So the next thing to choose is your electrolyte solution. What are you going to dissolve? You know, in general, a lot of the reactions we're looking at, you're dealing with cations. So for example, the copper 2+ cation. All you want to make sure is that it stays aqueous. So you just pair it with an anion that tends to be soluble. Sulfate is usually a good choice. Sulfates really have a high tendency to be soluble. Not all of them are, but you wouldn't want to do like copper sulfide, for example, because that's extremely insoluble. The KSP is really, really low. There's barely any copper cations that would be in solution. You want to get up to like 1 molar for your standard state, your standard conditions. You really want to be using something that's soluble. Sulfate is a good choice. Also, because sulfate doesn't do much redox chemistry. In much the same way that we used, say, sodium, potassium, because they were neutral cations, they didn't do acid-base chemistry. Sulfate is the same idea here in the context of redox chemistry. Sodium, still a good choice. Sodium cations do no chemistry at all, so we can use them in this case. They're just going to be there if you need a counter ion. So in this case, because your reactant is a cation, or if it's a product or reactant, it's a cation, you need an anion to go with it. You just choose sulfate. So that's how you would get it to dissolve in solutions. Participation 1111, question 1. Suppose you're making a cell based around the following reaction. Mg solid plus CD2 plus aqueous becomes Mg2 plus aqueous and CD solid. What solid could you use as the electrode for the anode half reaction? This is the first question on participation 1111, due Tuesday, November 11th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, suppose you're making a cell based around the following reaction: magnesium solid and cadmium 2 cations react to become magnesium cations and cadmium solid. What solid could you use as the electrode for the anode half reaction? First question on participation 1111. Plenty more videos to go, maybe more questions. See you there.